All right, hello. So in this video, I'm going to go over some basic patterns for searching through data using Python. Searching is one of the most common tasks that we do with computers, and particularly when we're working with a lot of data. And in fact, one of the things that computers are better at and do more effectively than humans do. Which is part of why we end up using computers to do searching. So this video is going to repeat a lot of what's in the course text, but I'm mostly going to walk through it verbally because I think it might help clarify sort of what the steps are going on. Okay. Slides. There we go. So the most basic idea when we're searching, the most basic kind of search, is that we're going to basically be searching, taking a list, and we're going to be searching through that list to see if a particular value is inside that list. So for example, if I have a list of numbers, like that I have down, you're not going to let me highlight, that I have down here, I might want to say, is the number 11 in this list, or is the number 12 in this list? I'm basically asking an in operation. So the basic approach that we're going to do this is using what's called a linear search. So the basic idea is we're going to imagine all these elements are sort of in a line. And what we're going to do is we're going to basically go through each element one at a time, checking to see if that element is the person that we're looking for. It's very much like we're lining them all up, and we're just going to go to the first person and say, hey, are you who I'm looking for? No? Okay. Next person, are you who I'm looking for? Nope. Okay. Next person, are you who I'm looking for? Nope, okay, and we're just going to keep going down the list until we either get to the end of the list, and in which case we didn't find anybody, or we find the person that we're actually interested in. This is basically, again, the equivalent of like going door to door looking for the person that we're interested in. The person we're interested in this case will be called the target. So the way that this code is going to end up looking like is we're going to basically say we're going to write our function that's going to do this work, and we're going to have a list, which is going to be all the elements we're interested in, and then we have our target of who we're looking for. The basic structure is pretty much just we're going to go through each element, and that means we're going to use a loop. So we'll just have a standard for loop. We'll just say for each element in the list, like for each number in numbers, or for each letter in letters, or whatever thing we're looping through. And then for each one of those elements, we'll see if that thing is the target we're looking for, right? So we're going to knock on the first element's door. We'll see if it's the right thing. If that's who we're looking for, then I can go ahead and I can return true from this method because I know that, yes, I found that element. I can go back and report that, yep, that guy we're looking for, he was totally in that list. And then what happens is that if I get all the way through this for loop and that if statement never occurs, then that means I'll never have returned, I'll never have exited my function, so that I'll go ahead and get to the last line of this function, in which case I'm done looping, I've gone through everything, I never found anybody, so I basically throw up my hands and say, great, he must not be in there, let's return false to say that's not done. So again, to sort of walk through this in process, like with a sort of a real example, if we call our function to look in our list of numbers for the number 11, we're going to go through all my numbers. These are going to be assigned to a list. So we'll go through element, and the first element will become 17. So we'll start with 17. We're going to say if 17 is equal to 11, and it's not. So therefore, that if statement doesn't execute. So we're going to swing back around, go back up to the for loop. Our element now becomes 18, and we check 18 is not equal to 11. So again, that if statement won't execute. Go back up again. The 3 is not 11, doesn't execute, goes back again. 7 doesn't execute, doesn't go back again. The 11 doesn't. We get to the 11, right? So if 11 is equal to 11, that's true. So in this case, our if statement will execute. We will actually run that return true statement, which means our function now exits and it produces a value of true because that's what that result is returning. So again, it's like we're sending someone out to go door to door and being like, try to see if this person lives on this block. They'll knock on every door, and if they get through every door, if they get to a door that has that person there, they'll be able to come back and say, yep, I found him. And if they get through all the doors but don't get to where they are, then they'll come back and say, nope, I couldn't find him. I checked every door and he wasn't in any of them at all. Cool. So that's the basic idea behind this linear search. We're going to go through each element. We're using this loop, and we're going to check each element one at a time. I'll note that it's possible to do this exact same kind of work using the built-in in operator. So rather than writing my own function that did this kind of searching thing, I could say check to see if 12 is in the numbers, which is doing the exact same thing as the previous line of code here. So you don't have to necessarily write this linear search yourself, but if you're trying to do something that's going to be a little bit more complex than just saying is a value directly inside a number, if we're trying to say is there some element that has a particular property, or if there's something else a little more complex going on, we may want to end up using this kind of searching algorithm. Right. So this is actually pretty straightforward, I hope, in that there's only like 4 steps here, right? We're going to loop through things, we're going to check to see if it's the target. If so, we return true, and then if we get to the end of the loop, we're going to return false. That said, it's actually surprisingly easy to have this, to make mistakes around this. the most common mistake that people end up making is that they try to return early. So what you'll do is they'll try to build the same loop, and they'll basically say, well, I wrote an if statement here, and for some reason they think that well, not for some reason, right? They think, okay, I built an if statement, therefore I must need to have an else associated with it, right? Well, what happens if it's not true? What should I do? You'll notice that in our sort of previous working version of the code, I have an if statement, but there's no else. It's just if I solve the guy, I return true, but my else is mostly the do nothing, keep going, right? Don't do any other changes, just continue with your current process, continue going through the list. So there's no else involved there. If you go ahead and you put an else in there, we say, okay, let's check, see if the element is true, then we'll see if the element's in the room, and then if they're not, if you then return false, it doesn't end up working. So let's walk through this example. So we've got our same set of numbers, and we're going to look for the number 11. So we're going to take our first number, 17, and that becomes our element. So we're going to say, is 17 equal to target 11? It's not, so therefore we don't get into that if, so we get into the else. The else then says return false. Well, we looked at the 17 and said 17 wasn't 11, so we went back and said, hey boss, nope, doesn't live there. There's no 11 in that list at all, which is clearly wrong because there's 11 right there. So basically what this is doing is if you say if the thing that I not looked for isn't the element, if you then immediately return false, then what you're doing is that you're sending off your person to go knock on every door. They knock on the first door, they say, hey, are you the person I'm looking for? And that first door says nope. And then they're like, oh great, must not live here at all, must not be anywhere on the block. They check one door and they leave, which is clearly lazy. That's not what we want to do. We'd like our person to be able to have to check every single door. So you can't actually say that no, this person is not in the list until you've checked every single element of the list. So a big part of keeping in mind as you're doing these kinds of searching algorithms, as you're writing these kinds of loops, is that when you're trying to determine if something is true or false, is you want to make sure that you're not making assumptions early, right? So you have to say, can I say with certainty that yes, the element is not in that list? And the only way you can do that is if you've actually looked at every single element, or there's some other circumstances that might be going on. Okay, great. So yeah, again, the main idea here is you don't want to use there's no else statement involved in this general algorithm. It's just that I'm going to go through every element, check to see those ones, and if I find someone early, then I can return true, but otherwise I need to wait until I get all the way to the end, I'm outside of that for loop, and then I can go ahead and return false. All right, so there's a couple of other variations we can do with this. Often what we're going to be interested in doing is not knowing necessarily just whether a person lives on that block, or whether that person is in the list. We want to know where they happen to live on this list. So this is going to use basically the same process. We're just going to change our loop a little bit. So that instead of going through all the different elements of the list, we're going to go through all the different indices of the list. We're going to loop through the room number. So rather than saying I'm going to go check every person who lives in a house, we're going to go say I'm going to go check every house number and knock on each of those doors. So again, the only thing that's changed here, so you look from the previous loop, is that we've changed, so rather than looping through a list, we're now looping through the range to the length of the list, going through each index, and then we're going to not be comparing the index to target, because remember, index is going to be what element we're on. We're not interested in if the room number is the target, we're interested in the person who lives in the house. So we're going to make sure that we access the element at that room number, right? Go to a list bracket index, and that's who we're going to want to check against the target. And if so, if we knock on that door, we say, hey, who lives at door number 3? And 11 lives at door number 3, then we can go ahead and return that door number. We can say, hey, yeah, I found the person I'm looking for. They were at room number 3. By convention, if we get to the end of the loop, so we check all the doors and we don't find the person we're looking for, what we'll often return is we'll return a value of -1. The reason we return -1 is because if they lived on the block, right, their room number, their house number would be a value from 0 to the length of the list, right? Because they might live in house 0, they might live in 1, they might live in 2, 3, 4, 5, 6, 7, up until the length of the list. And that length of the list can be really, really long. We don't know what it's going to be. So what we tend to do is we tend to return -1 because that's basically saying that that's not going to be within the normal range. It's not going to be between 0 and the length of the list. It's outside of that, right? It's beforehand. It's like an invalid entry, effectively. So if we return -1, it's a way of saying that no, they didn't live in the list. We can do that by convention. There's other options you could do as well. You could return none or false and some work, but generally you return _1, at least produce it so you still have a number. What you could end up doing is if you really want to know if somebody's in the list, you can do that search, right? Check to see if they're in the list, so look for our 12, and then I can compare that value to 0. So I can say that if they're sorry, I lost my train of thought. So if we can check that, see that value, and if it comes back and if it's a -1, then we know it's not going to be, it's going to be less than 0. So therefore, effectively we can use this comparison to 0 to determine whether somebody's actually in the list, because we can check to see if the value we got was an actual room number or whether it was sort of the like default blank -1 kind of thing. Okay, great. So let's see what's next. So this is the most this kind of searching, right? We'll go through everybody and see if they're there. Is the most basic kind of searching that we're going to do. It's the simplest structure of this algorithm. It's the same basic approach, and then we can start doing other modifications if we want to start getting more different kinds of information. The second most common kind of thing that you might want to end up doing is you might be interested in figuring out which item is the biggest. And this is what I refer to as a maximal search. So we're interested in basically figuring out sort of what's the maximum value of a thing. And I want to make sure that maximum doesn't necessarily only refer to large elements. So this could be the biggest number, it could be the longest word, it could also be the shortest word, it could be the fastest turtle, it could be the highest scoring football game, it could be the lowest number of errors in a baseball game. I don't know why I have sports on the mind. But basically it's going to be anything that's going to be sort of the mostest value. And that could be the biggestest or the smallestest. It's going to be anything that's sort of at the extreme end of some kind of ordering. So the idea is if you sort of, you take all our elements, you put them all in order, either ascending or descending, right? Either big to small or small to big. If you're looking for that thing at the start or the end, depending on your point of view, that's this maximal search. So in this case, in our example, we're going to look for what's the biggest number. So the algorithm that we use to do this is what I refer to as a king of the hill search. And it's called a king of the hill search because it's named after a sort of children's playground game called King of the Hill. In this game, you'll have you basically have there's a hill of some kind or some kind of mound or something, and some child will basically go up to the top of the hill and they'll declare themselves they are the king, they are the current holder of this hill, and then all the other kids basically come up and try to knock that kid off the hill so they can become king, and whoever ends up being the last person standing ends up winning. So that's basically the idea we're going to do. So we're going to basically put one person on the hill. We're going to say that person is currently the biggest, that's the maximum, and then we're going to have everybody else line up to challenge him, basically, or challenge her, challenge that person. So the next element in line is going to come up to the hill. They're going to have a contest. They're going to see who wins. And if the person who was originally on the hill continues to win, they continue to be the king, they stay there, they're still the maximum. But if that other person in line, if that challenger ends up winning, then they usurp the crown, they become the new person who's in charge, and then the process repeats. So effectively it's going to be, we're going to have one person who's sort of the current champion, and then everybody else is going to come up and attempt to challenge that champion, and then once we've gone through everybody, whoever ends up being the last person standing, whoever was the person who did not get beat by anyone behind them and was able to, in theory, beat the most powerful person before them, is able to win and be considered the maximum value of this that we're looking for. All right, so let's go sort of run through this example and see how this works. So we're going to have our same list of numbers, and we're just going to keep working the same list. So we're going to take the first element, the first person, so the 0th element, and we're going to call that person the king. That's our maximum value. So at the moment, 17 is going to be my top value. We're then going to go through each element in the list. We're going to start with the 17. Fine. The 17 will compare it to himself. So basically, the 17 has to challenge himself because it's easy to write the loop that way. The 17 doesn't beat himself because it's not bigger than himself, so the 17 ends up remaining as the king. Life is good. We get to the next element. We get to the 18, right? So our element is now 18. We're going to take that 18, compare it to the current winner, who's 17. 18 is bigger than 17, so therefore the 18 is going to become the new winner. So our winner is now 18. That's our biggest value. We're then going to go to the 3. The 3 is going to compare himself to the winner, the 18, and doesn't win. So therefore the 18 continues to be the maximum. And then all these other numbers are going to go along the way, and so that eventually none of these other later numbers are going to be able to beat that 18. So therefore, the 18, after we finish going through the loop, we'll return that 18 as the biggest value that was available to us. So that was the biggest value in the list. Yeah, that's the basic approach. That's going to be we're going to say take the first element, call it the winner, then go through everybody else, have them compare themselves to the current winner, whoever is currently winning. And if they are better than the current person, then they win. Then they become the new winner, and whoever is on top at the end is who we return. Excuse me. The most important part of this, and the biggest mistake that people make, is you want to make sure that you're comparing the element to the current winner. We don't want to compare the element to the next person in line or to the previous person in line, because it doesn't matter how I necessarily compare to the person before or after me in line. What matters is how I compare myself to the person who's winning at the moment, who's actually on the hill, right? So it doesn't matter if this 7 is bigger than the 3, because the 7 is going to be less than the biggest person who's already on the hill, right? It's like, yes, I'm better than the person in front of me in the list, but I'm not better than the person on the hill, and that's the thing that we actually care about. So what we want to do is you want to make sure you're comparing to the maximum, not comparing to some other element inside the list. All right, cool. Good. So, oh yeah, and again, if we want to know where the biggest element was, if we want to know which index he was in, like we want to know like what house number is the biggest kid happened to live in, we can do the same thing where we could say, let's loop through all the indices in my list, and we'll just access the element by going to, for a list bracket index in order to be able to access that particular element in the exact same way. Everything else about the maximum stays exactly the same. All right, so the last variation of this search process that we want to do is maybe to ask a question about all the elements. So for example, maybe we want to ask if all the numbers are big, if all the kids are large or old or whatever, if they're all wearing hats, if all the turtles are fast, if all the dogs are good boys. We want to be able to ask questions about every element in the list. Now, this linear search process only really is because using a for loop, it only really works for one element at a time. It allows us to look at one thing, right? I can look at one dog or one number, but I can't necessarily determine that, but just looking at one number doesn't tell me anything about the numbers around it. So I might say, look at this one dog and say, yes, that one dog is a good boy, but that doesn't tell me anything about the other dogs, so I can't make some claim about whether all the dogs are good. I mean, other than the fact that they must be because they're dogs, but I can't make some claim about all the numbers being big if I haven't looked at if I'm not actually looking at all the numbers. So the way that we end up thinking through this is that if we're trying to ask a question about all the items, and I want to know if some truth holds for everything, right? All numbers are big, all dogs are good, then the way we're going to do is we're going to invert the question a bit. So rather than trying to look at every single element and be like, yes, are you what I want? Are you in fact good? We're going to try to basically look for instead, we're going to assume that everything is what we want. Everything is big, everything is good. And we will then instead try to see if we can find a counterexample. So what we'll do is we'll actually say, let's assume all dogs are big, and let's go through and look at all our dogs and see, can I find a counterexample? Can I find a dog or a number that is small? Can I find a dog that is not good? And if I can find that counterexample, then I know that, oh, I found something that broke my assumption that I found this counterexample, therefore I know that all my items must not be big, all my dogs must not be good, because I found one that wasn't the case. If I go through my list and I can't find any contradictory evidence, then I can assume that, yep, everything is big, just like I hoped it was going to be. So it's basically the idea is we're going to sort of switch from asking, are all the numbers big, to trying to ask, well, is there any one number that might be small? Because the inversion, the logical negation of an all statement is an any statement. So rather than saying that all numbers are big, the negation of that saying is there must be at least one number that's small. Not that all numbers are small, just that one might be small. So that's what we're going to basically do. So we're going to ask if all the numbers are larger. We're going to start by assuming, because that's our positive statement, right? We want to know, is all of them big? That's what we're trying to find. So we're going to assume that's true. All numbers are large. And we'll make a variable, a Boolean, that represents that. We're going to assume that they're currently all large, and we'll say that's true, because really, at this point in this code, at line 2 here, all the numbers are big. Every number I've looked at has been big, because I haven't looked at any number, so therefore they're all big. We'll then go through all of our elements and look for a counterexample. We'll do that by saying, rather than looking to see if the element is above some minimum, if it's a big number, we'll actually look to see if it's the case that that's not what's going on. If it's not the case that the element is greater than our minimum. We could, of course, have written this if element is less than or equal to minimum, so we could have just inverted the comparison, but I kind of like using the not as a way of clarifying what's going on here. I'm literally saying if it's not a big element. And if so, then I might say, oh, it's not a big element. I found my counterexample. My all large must now be false, right? Because they're not all large anymore, because I found one guy who's small. And because I've now found someone who's small, I now know that we're done. We found our element. If we want to, we can keep looping through them and keep checking to see if there's anyone else. If we find someone else who's not large, we'll once again assign all large to become false. Notice that inside this for loop, all large never can possibly become true. So it starts out as being like, this is truth, and as soon as we find a counterexample, it flops, and it never can go back. So it never can be. So if we found one counterexample, we can never make that statement true again because that counterexample exists. If we want to exit the loop early, we can use a special statement called break, which basically says stop running through the loop and just immediately go to the end, pretend that you've already exited, you've already finished going through all the elements. I'm doing that mostly just for speed here. And then finally, we'll have our function actually return whether our assumption held or not. So if we never found a counterexample, then that means our all large would never have changed. It would have started out true and stayed that way through all the evidence we possibly could look for, right? We checked every possible counterexample and we didn't find any, so therefore we stay true, so we return that as true. If when we're going through we found a counterexample, right, and suddenly stuff's changed, then we will return the fact that it is now changed and we can be good to go and we're done. So again, this is going to do the exact same kind of work that we expected. We can ask if all the numbers are larger than 10, which will be false because when we go through we find that 3 is a counterexample. If we then ask if all the numbers are larger than 2, we're going to go through and none of these will be counterexamples, right? For none of these elements will make this if statement be true, right? Because it's never not the case that our element is bigger than 2. So therefore, we're going to return true and the whole thing will all be done. And that's the basic idea behind searching. So these are all examples of what are called linear searches. You can think of it a little bit because I say it's almost like we're lining people up. We're sort of going down the line. And that's a good way of sort of remembering that it's a linear search, right? It's not like lining people up. Though more accurately, they're called linear searches because really this algorithm is going to scale proportionally with the data size. So as I add more houses or more numbers, more people, I have to do a proportional amount of work to check every single person because again, I'm just going down the line for them. There's some more details about how this kind of learning a search process might impact things like searching and program efficiency. It's sort of an advanced topic that's covered in the course text. But this is going to give you your basic structure for how I can search through a list for values I'm interested in. Either particular values, either searching for most maximal values, or if I'm trying to say ask some question and search through all the list for say maybe a counterexample. As long as you can think about the idea of line up all the values and go through each one and look to see if you find the one you're interested in, that will let you be able to search through lists and find the data that you're looking for.